why do adjacency matrices always have an eigenvalue of 1? Why is that? You know what? This is a good question that I want you to think about with the people near you. The hint I will give you is think about how eigenvalues relate to determinants, relate to matrices being symmetric, relate to one of the properties that this matrix has to satisfy, involving the number 1. Okay? Discuss with the people near you for a minute or so. Why do we know for sure that any adjacency matrix that is valid has an eigenvalue of 1?
The trace converges with one. So we points out at minus. They maybe like in the long run the trace.
What is any ideas?
Good. That's special. Yeah, like 0.6. I'm not too sure. You can do 0.9.
Okay. What's our current thinking? Why do we know for sure adjacency matrices have to have an eigenvalue of 1? Why? You don't have to have the full answer, but just tell me what you're thinking. Tell me the main property of an adjacency matrix that you think will be relevant to this.
Well, the determinant of A is equal to the determinant of A transpose. So we can multiply the vector, like the 1 vector, by A transpose. And the rows of A transpose add up to 1. So the result of the matrix multiplication of A transpose and the 1 vector is the 1 vector.
Good. So you stitched all the pieces together, and that's indeed how we know that this is the case. Let me take a step back, though. The key observation you use there is that the columns add up to 1. That's what makes this an adjacency matrix. Right? The numbers themselves are non-negative, and they add up to 1. So the columns themselves are valid probability distributions. So observe. The columns add up to 1. Then observe. As Sina mentioned, if you take the transpose of an adjacency matrix, which is going to look like here, 0.8, 0.2, 0.3, 0.7, and multiply it by a vector of 1s, which is that special tool I've told you about lots of times throughout the semester. You use a vector of 1s whenever you want to add up the things in a different vector. When you multiply a vector of 1s by A transpose, what do you get back? A transpose times 1, 1 is what? Yeah, it's just 1, 1. What does that tell you? It tells you 1, 1 is an eigenvector of A transpose with the eigenvalue of 1. Here's the key. A and A transpose have the same eigenvalues. Not the same eigenvectors necessarily, but the same eigenvalues. Why is that? I won't write it down because, again, I want you to read the notes for the details. But why do A and A transpose share eigenvalues? This is more of an algebraic fact than anything. Yeah, Swati.
Because I is get that
Yeah, it's because they have the same characteristic polynomial, right? The eigenvalues in each case are the roots to a minus lambda I equals, sorry, the determinant of a minus lambda I equals 0 for A, and the determinant of A transpose minus lambda I equals 0 in the A transpose case. But the determinant of A and A transpose are the same, and I and I transpose are the same, and so the characteristic polynomials are the same. That's the key. I'll say they have same characteristic polynomial for both. And so because A transpose for sure has an eigenvalue of 1, A for sure has an eigenvalue of 1. All right? But it turns out that knowing that A has an eigenvalue of 1 isn't enough to fully justify why this system converges to the eigenvalue of eigenvector with eigenvalue 1. Let me say that again. What we just argued is that any adjacency matrix for sure has an eigenvalue of 1. 1 is one of its eigenvalues. That means we can find a vector whose eigenvalue is 1. That's for sure for any adjacency matrix. What additionally is true and needs to be true in order for this statement to hold, that the system converges to the eigenvector whose eigenvalue is 1, is that not only is 1 an eigenvalue, it is the biggest eigenvalue of the matrix. That is the key. It turns out that the biggest eigenvalue of a matrix determines its long-run behavior. Okay? And so, to really see what I mean by that, I want to switch to a different example, one that doesn't involve adjacency matrices. It's that first example that we saw earlier when I had you work on that warm-up activity. 3, 1, 2, 4. Okay, what were its eigenvalues and eigenvectors? We had an eigenvalue of 5 with a vector of 1, 2, and an eigenvalue of 2 with an eigenvector, think of 1, negative 1. And here's my question now. This is not an adjacency matrix. Here's my question. What does a to the k times x0 approach as k approaches infinity? Firstly, okay. You know what? This is another opportunity that I want you to stop and discuss here. Notice that unlike in the adjacency matrix example, the numbers aren't all fractions less than 1. So imagine if you start with any vector, like if x0 is just, I don't know, 1, 1. What is the next vector going to be? 4, 6. What's the vector after that going to be? Like 18 and 24 or 26 or something like that. The numbers are going to keep getting bigger, which is not what happened in the adjacency matrix case, right? In the adjacency matrix case, as long as we started with a vector whose numbers added up to 1 and weren't negative, the numbers in the adjacency, in the state vectors, x1, x2, x3, x4, they didn't explode. They stayed small decimals. That's not going to happen here. Okay, here if you multiply, if you start with any state vector, the numbers are going to explode. But there still will be something predictable about their behavior. And what I want you to think about, without referencing chapter 9.3 where the answer is think about what happens. This still converges to something predictable. But what is that something? Discuss.
One of the eigenvectors. Something in one of the eigenvector, right? Start with 46, right?
And then
It's gonna end up like the values, like 5 or 2, like a product of those. product with A times X naught. It becomes some kind of like.
Oh,
vector,
oh,
you know what I mean?
okay, yeah.
Like, if X naught is arbitrary,
Yeah.
it doesn't matter.
Yeah, because it's going to compare like, oh, they said that before.
You just start at 1, 2, 4. You go on,
The vector with the biggest eigenvalue.
Yeah.
and then keep scaling
That's what he said.
some
Yeah. But I don't know.
I feel like there's gotta be some visual.
X is A
Do
times.
you know it's fate has
A itself is giving a function that it scales by So if A is made up of like some kind of eigenvalue, then I think that eigenvalue can describe how it scales over time.
Yeah.
That's not.
Interesting.
I mean, I don't, no, because I don't, I don't have an idea yet. So I'm just like,
Feels like it all works.
Yeah.
That's my favorite. What do you think, dude?
I think it's gotta be. Maybe like points in the direction.
That's what I was saying. I was gonna say since X naught can be arbitrary, then the matrix A, the important factor. Because like if any vector X converges to that same behavior,
Okay, what's our prediction?
then A, which is made up of
So to be clear,
value,
I'm saying start with any initial state vector.
will scale it repeatedly.
The numbers in it,
I don't know.
as you multiply it by a, and then a squared, then a cubed, then a to the 4, are going to explode. But the direction of the state vector does approach something. The direction of the state vector approaches what? Any guesses? Any guesses? I have a diagram for you here where we simulated this. What did we end up seeing here? So this is the same matrix A, 3, 1, 2, 4. Started with a random state vector, negative 13, comma 100, just to emphasize that it could really be anything. As you simulate and advance steps in the future, right, this x to the 15 is really just a to the 15 times negative 13, comma 100. The numbers in it are massive, but they fit a pattern. They fit a pattern. What is the pattern? Charlie.
Eigenvector 1, 2.
It's the eigenvector. It is an eigenvector, yes, of what?
1, 2.
And what is special about the eigenvector 1, 2? Bless you. Indeed, that was the right observation here. Note that as these numbers get bigger and bigger, the second number looks like double the first one. That's not the case, I mean, to start off with, definitely not the case. 100 is not anywhere near double negative 13. And even in the first case, 374 is way bigger than double 61. But as we iterate more and more, the second number looks a lot like just the first one times 2. And so these vectors, as we iterate more and more steps of this process, start pointing in the direction of the vector 1, 2. Right? They're way longer than 1, 2, but they're just a scaled multiple of it. Do we buy that? And what's special about the vector 1, 2? What's special about 1, 2? Yeah.
It has the biggest eigenvalue of 5.
Exactly. 1, 2 is the eigenvector of the biggest eigenvalue. To be more precise, I should say biggest in absolute value. If this were negative 5, I'd still say see the same behavior. Okay? The key here, which is the key in the adjacency matrix example, is that the long run behavior of the system depends on the largest absolute, or the largest eigenvalue in terms of absolute values. Okay? Here, the numbers exploded, but they point in the same direction as 1, 2. Why do they point in the direction of 1, 2 and not the other one? Well, it's because 5 is larger than 2. That is the reason. So 5 is what we would call the dominant eigenvalue here. Approaches the direction of the dominant eigenvalues eigenvector. So the number 5, which is the eigenvalue with the biggest absolute value, doesn't appear anywhere on this page, right? The number 5 is not particularly important. What matters is that 5 is the eigenvalue with the biggest absolute value, okay? That's what dictates where the system is going to converge, okay? Now your question may be, why is that the case? Like, the number 5 didn't appear anywhere here. We didn't start with the vector 1, 2. We started with some random numbers. Well, like, why did this converge to the vector 1, 2 in terms of direction? Perfectly natural question. It's not clear at all, right? And until I taught this class for the first time and did this proof that we're about to do for myself, I didn't believe it either, but we're about to believe it. Here's another cool way of looking at what happens here. All I've done here is I've just plotted out the guess vectors, x1, x2, x3, x4. And you can see they all start lying on this line, y equals 2x. Because that is the line spanned by the vector 1, 2. Okay. So why is this happening? So why did a to the k x0 converge in direction to the eigenvector with the largest eigenvalue? Why did this happen? Well, yes,
I have a question.
of course.
What if the dominant eigenvalue had a geometric multiplicity of like 2, for example? Would it just be anything?
Good question. So let's save discussing that until after class or Wednesday, because we're not going to talk about algebraic or geometric multiplicities until Wednesday. But they'll be a natural lead up after what we're about to do. Okay. My question for now is, why did this happen? And so here's how I want to set up this argument. Suppose x is just any vector in R2, not necessarily an eigenvector. Okay, let's use this matrice's specific eigenvalues and eigenvectors to illustrate, but suppose x isn't necessarily one of the eigenvectors, it's just some other vector. Let me make this smaller. It turns out I can write x as a linear combination of something. What can I write x as a linear combination of? What am I getting at here? Doesn't matter what x is. There's something that guarantees that I want to see if you can piece it together. I'm intentionally being a little vague here. I can write x as a linear combination of what? Yeah.
Eigenvector.
Yeah, I can write x as a linear combination of these two things. Why is that? I can write x as a linear combination of 1, 2, and 1, negative 1. Why? Why is that for sure? Yeah.
Because
V1 and V2 are like both in R2 but linear independent.
Yeah, exactly. V1 and V2 are two linearly independent vectors in R2, so I don't need to know what's in X. I know I can make it with V1 and V2. So V1 and V2 are linearly independent. And span all of R2. So it must be possible to write X as a linear combination of them. Do we agree with that? Doesn't matter what X is, I can make it with V1 and V2. So why don't I say X is equal to, I'm not going to use the coefficients of lambda 1 and lambda 2, because that's not necessarily true. But why don't I say X is C1 V1 plus C2 V2, where the V1s and V2s are coming from here. Don't really care what the C's are. For this argument, all that I really care about is that I for sure can do this. We agree with this? Here's my question. And so I have X equals, let me use the same color as the last slide. X equals C1 V1 plus C2 V2. Here's a question. What happens when I multiply X by A? What happens when I multiply X by A? I don't know, let's do it. Then I'll get AX equals A times C1 V1 plus C2 V2. But I can distribute the multiplication by A and write this as C1 times A V1 plus C2 times A V2. What does this simplify to, though? What does this simplify to? Remember, what are V1 and V2 here? What are V1 and V2? Remember, V1 and V2 are what? Yeah.
Just replace A with the corresponding eigenvalue.
Exactly. V1 and V2 are eigenvectors of A. And their eigenvalues were lambda 1 and lambda 2. So why don't I write this as C1 lambda 1 V1 plus C2 lambda 2 V2. What was the point of this? The point here is to emphasize that if X was a linear combination of the eigenvectors, AX is also a linear combination of the eigenvectors, just a different linear combination. The old weights used to be C1 and C2. The new weights for AX are C1 lambda 1 and C2 lambda 2. You agree with that? All right. What do you think would happen if I hit this, that is, multiplied it by A again? So if I multiplied both sides of this by A, what would result down here? So like, what I'm asking is, what is A squared X? What's the same, what's different?
The lambdas just be squared.
Exactly. All that would happen is if I distribute a multiplication of A through this piece down here, C1 lambda 1 V1 plus C2 lambda 2 V2. The C1 lambda 1, those are constants, and multiplying A by a V1 just turns that into lambda 1 V1. But I already had a lambda there, so this just becomes lambda 1 squared. So this becomes C1 lambda 1 squared V1 plus C2 lambda 2 squared V2. Do we buy that? That's the beauty of lambda and V being eigenvalue eigenvector pairs. Multiplying by a matrix equals scaling by a constant. It reduces the complexity of the situation by a lot. So in general, instead of the number 2, what if I say a to the power of k, where k is some integer? What changes? What's the same? What does this expression on the right-hand side become? If instead of a squared, I'm looking at a to the power of k. What do I get? It's still c1 something v1 plus c2 something v2. But what is that something? Charlie?
Lambda k.
Yeah, the lambdas get exponentiated to the k. This is the key here. And remember, our goal was really just to understand, as k gets bigger and bigger, what happens to a to the kx, right? So our question is, what is the long run behavior of this thing? But now I've kind of reduced the problem into thinking about what is the long run behavior of this expression on the right. How is that any easier? Well, let's think about it. Okay? So the question was, as k increases, what happens to a to the kx? And we know what the answer is going to end up being, because we saw this like intuitive picture and experimental result, which is somehow this has to relate to the biggest eigenvalue, somehow. Or the answer is going to end up being that the direction of this vector is the same as the direction of the eigenvector with the biggest eigenvalue. How do I show that? Yeah.
Well, as it gets so large, you can neglect the one that has a smaller eigenvalue, because in the long run, the other one's going to dominate.
Yeah, but how do I see algebraically that that's what happens? You're exactly right. How do I see that algebraically? Yeah.
You can just assume like one is bigger than the other and then divide by the bigger one.
Exactly. So just to make it a little more concrete, let me just plug in what the two eigenvalues are here, okay? So just to illustrate, use lambda 1 equals 5, lambda 2 equals 2. So what does this become? I have a to the kx equals c1, we'll stick with 5 to the k first, though the order doesn't really matter here, plus c2, 2 to the k, v2. And indeed, the answer is that the 5 to the k piece is way bigger than the 2 to the k piece. How might I see that? Well, one thing I can do is divide both sides of this expression by 5 to the power of k. What happens when I do that? What I'm left with is the vector who I'm trying to describe, which is a to the kx. That over 5 to the k, that is just a scaled version of it, is c1 v1, because 5 to the k over 5 to the k cancels out, plus c2 times 2 over 5 to the k v2. But as k grows, 2 over 5 to the k shrinks. And so what that shows you is that as k approaches infinity, the direction of a to the kx ends up being solely determined by v1, which was the eigenvector for the bigger eigenvalue here. Because the other smaller eigenvector, smaller eigenvalues and their corresponding eigenvectors, their influence gets smaller relative to the bigger eigenvector's influence. Okay, and so here I divided by 5 to the k, but there's nothing special about the numbers 2 and 5. Whatever the largest eigenvalue was in terms of absolute value, I could just divide both sides by it to the power of k and repeated this analysis. So the eigenvalues could have been 4 and 5. And I would have had the same logic, right? 4/5 to the k still approaches 0 as k gets bigger and bigger. The eigenvalues could have been -5 and 2. And the direction would still approach that of the bigger eigenvalues eigenvector in absolute value. Right? -2/5 to the k would also approach 0. Right? So this analysis shows you that the direction of a to the kx approaches direction of the largest eigenvalues eigenvector. Do we agree with that? Okay, so it turns out with any matrix, the eigenvector corresponding to the biggest eigenvalue tells you a lot about how the matrix works in these sort of dynamical systems. Okay? The dynamical system we care most about is an adjacency matrix for which the biggest eigenvalue is 1. So just to recap, an adjacency matrix, it is defined by having non-negative entries and columns that add to 1, and it represents a Markov chain, which is a system like this one. And in an adjacency matrix, it is guaranteed that not only 1 is an eigenvalue, but it's also guaranteed that 1 is its biggest eigenvalue, which is why for sure these long-run systems converge on a valid probability distribution corresponding to the eigenvector whose eigenvalue is 1. Now, the one thing I didn't actually prove here is that 1 is always the largest eigenvalue. All we discussed is that 1 is an eigenvalue, but not necessarily that it's the largest. That it's the largest requires a little bit more theory than we are going to discuss, but there's a theorem linked in the notes called the Perrin-Frobenius theorem that shows why 1 is also the biggest eigenvalue in addition to being an eigenvalue. Okay? So that's sort of it for our discussion of adjacency matrices and Markov chains. And in lab and homework this week, you're going to see several examples of this. So one of the examples in lab, it's kind of cool. This theorem guarantees that 1 is the largest eigenvalue. And using the logic we just discussed, if 1 is an eigenvalue and something smaller than 1 is an eigenvalue, well, then the long-run system will converge to the eigenvector for eigenvalue 1. Something I didn't realize when making the lab question last semester is that we gave you an adjacency matrix where the other eigenvalue was -1. Okay? And if you have eigenvalues of 1 and -1, then this analysis here of there being one eigenvalue that's bigger than the other doesn't really hold, because 1 and -1 are of the same size. And so in that question, if we keep that question in the lab, what you'll see is that there isn't actually a steady state distribution. It keeps flip-flopping between 2 possible steady states, which is what happens when there's 1 and -1. Okay? Here's where I'll end off. In this analysis, what did we assume about the vectors v1 and v2? Right here we said just x is something in R2. What did we use about the vectors v1 and v2? Yeah. Yeah, here we relied on the fact that x for sure could be written as a linear combination of v1 and v2. Okay? This matrix, 3, 1, 2, 4, has the property that it has 2 linearly independent eigenvectors, meaning you can span all of R2 with its eigenvectors. That's a nice property that it turns out that not every matrix has. There are matrices for whom their eigenvectors don't span all of R2. Okay? And that is the central problem to Wednesday's lecture. The short answer, if you want to look at the titles of the lectures, is that a matrix is diagonalizable if it has n linearly independent eigenvectors. And we like diagonalizable matrices. This matrix A, 3, 1, 2, 4, it is diagonalizable. You want an example that's not? 1, 1, 1, 0. Try and find its eigenvalues and eigenvectors. You'll see that you can't find 2 linearly independent eigenvectors for this matrix.